Welcome everybody to the fifth and last chapter of this lecture series with the title Damage Controlled Forming Processes. My name is Jan Gerlach and I'm a research associate at the Institute of Forming Technology and Lightweight Components, and I'm also part of the TRR 18080 within the service project SO1. And besides my role in the SO1 project, I'm also part of the working group Damage Definition and Transfer to Education. And I'm happy to give you an overview and introduce you this following chapter. So, as you have learned in the previous chapter, Introduction, Damage Mechanisms, Damage Characterization and Damage Modeling, we have now all these tools at hand to identify and assess the amount of damage in formed parts, and also to analyze the effect on the product properties. And now I would like to give you an overview on some examples for the bulk forming route as well as for the sheet metal forming route. For both routes, we can classify, or we have structured the following slides in 4 subchapters: damage and forming processes, then the properties of the formed products, so sheet products as well as bulk metal formed products. Then we will discuss how we can control the damage by adapting the manufacturing process itself. And finally, we will discuss the final product performance in terms of crash capacity as well as the fatigue life. We will classify, or we would classify this entire chapter in advanced bachelor level as well as basic master level. Beginning with the bulk forming route, we will show you at first the classical process route for case hardening steel, with beginning of continuous casting, then a heat treatment, then followed by a caliber rolling and an additional heat treatment, followed by cold extrusion, and then there are some additional manufacturing processes such as cutting of holes and additional heat treatments after we obtain the finished product under service loads. For the following example, we assume that the heat treatment does not affect the properties between the caliber rolling and cold extrusion, and we just consider the material properties such as strain hardening and damage after caliber rolling for the subsequent cold extrusion. Beginning with the caliber rolling, we have some initial process parameters, such as the initial diameter of 60 mm. This will be reduced by caliber rolling within 4 passes to a diameter of 40 mm, and during the entire process the part is heated to a temperature of 1100 degrees of Celsius. The process itself was performed at the IBF at the RWTH Aachen University, and the subsequent simulation and cold forging has been done in Dortmund at the Institute of Forming Technology and Lightweight Components. Here in addition, some relevant process parameters within the simulation. Friction coefficient of 0.3 was considered, as well as the roll radius of 200 millimeters. And the strain extrusion, or not extrusion, the rolling strain reached from 0.25 to a minimum of 0.11 from pass 1 to pass 4. And this has been simulated, and as you can see here, the damage evolution is the highest on the outer surface. For simulating this, we considered a Lemaitre damage model, and this has been calibrated with different calibration strategies. So for the plastic behavior, we considered some isotropic hardening, and the flow curve was determined by some compression tests. For the damage evolution, we have considered tensile tests to calibrate the relevant parameters here. After the caliber rolling, some cutting procedure has been performed because the cross section is not perfectly round, and therefore we have to cut the specimen to perform the subsequent cold forging. And as you can see here in the dashed line, this was our initial radius, and after the caliber rolling we have a reduction to 40 millimeters, and this has been and then we have an additional reduction of the diameter by cutting to 30 millimeters. And the advantage of this cutting is that at first we have reduced in the residual stresses, so a stress relief by the cutting processes, and then on top of this the outer material where the damage evolution was the highest is also cutted away. So at the end the maximum damage in the part is 0.1.3. But after cold forging we have a strong increase in the damage evolution, and this is much higher compared to the value in the outer area. Much higher than the values after caliber rolling, and therefore we can say that the damage increase in caliber rolling is negligible for the subsequent cold forging. So for the point of view of the industry, we would say that this is not mandatory to consider the caliber rolling in the simulation as well, or the process route in terms of the simulation. But this is not this does not directly holds for every forming process. So you have to make some detailed analysis to perform some detailed analysis of each forming process if it is possible to neglect some forming process within the simulation. As we have seen before, the damage evolution and caliber rolling can be neglected, provided that the heat treatment in between the caliber rolling and the forward rod extrusion process has no impact on the material properties. Therefore, in the following we will only consider the forward rod extrusion process from the simulation as well as experimental perspective. When we consider a cylindrical billet in forward rod extrusion, the material properties of this billet during the process can be affected or controlled by the process parameters. And the most important process parameters are the reduction area, so the extrusion strain, as well as the shoulder opening angle, which is located here. And with the shoulder opening angle we can control the stress state, while with the extrusion strain the strain hardening can be controlled. When it comes to the investigation of damage and how damage solely affect the mechanical properties, we have to ensure that the mechanical properties, the material properties, are separated from each other, because different strain hardening have also an impact on the product performance in terms of fatigue life or Charpy impact toughness. And therefore, in the following, I would like to introduce how we could ensure that different parts have same residual stresses, same strain hardening, but different amount of damage, so that we can say the part with more damage has a less fatigue life performance, for example. At first, let's have a look on the separation of strain hardening from the considered specimens. For this, we extruded 3 different parts where we stick to the same extrusion strain of 0.5, but different shoulder opening angles. And as you can see here, for different shoulder opening angles, the strain hardening is at the beginning from the inner radius the same. Only for the outer surface the strain hardening differs, but this is not a problem since we manufacture tensile test specimen out of our extruded components to assess the fatigue life as well as the performance afterwards. So in the area of interest, so within the specimen which is manufactured out of the extruded components, we can ensure that the strain hardening is the same. One additional information when it comes to the separation of effects. In most of the cases we only consider one specific extrusion strain, because then we can ensure that the strain hardening on the central axis of the specimen is the same. Only when we have some perfect plasticity, like it is the case for the 6-wing Mancro 5, we have the same strain hardening for different equivalent plastic strains, which enables that we can also compare parts with different extrusion strains. But this is not the case here for the considered 16 Mancro S5. After we have ensured that the strain hardening is separated for different shoulder opening angles, we have to ensure that the residual stresses are the same, or better, are negligible small. And on the left hand side you can see the actual stress distribution and the extruded part, once for the ejection and in addition after the ejection. And even though there is no huge plastic deformation in the ejection step, we have a huge decrease in the residual stresses. And this is also shown on the right hand side. We have a maximum negative residual stress in Z direction of -200 megapascal and a maximum of 100 megapascal. But for the subsequent analysis of the fatigue life, for example, or the crash performance, we cutted specimen out of the extruded billets. And this is shown here on the right hand side. So we cut the billet so that we have just the same radius as in the slide before of 2.5 millimeters, and to ensure that equilibrium is achieved, the residual stresses have to move up, as it is visualized here on the right hand side. So at the end there will be a maximum residual stress from -50 and in a positive regime of around 30. And with this at hand, we can say the residual stresses can be neglected, as for an extrusion strain of 0.5, the yield stress is around 800. So with these residual stresses, we are far away from additional plastic deformation. And since we consider ductile damage can only increase during plastic deformation. So in the previous slide we only considered the extrusion strain of 0.5, and we have shown that for this extrusion strain we can separate effects such as strain hardening and residual stresses with varying the shoulder opening angles. So we are now able to manufacture parts which have the same amount of strain hardening and residual stresses, but different amounts of damage by changing the shoulder opening angle, because the shoulder opening angle affect the stress state. But the stress state can also be affected by different extrusion strain. Here the disadvantage is that we not directly have the same strain hardening, but to complete the entire picture, I would like to introduce you also the effect of the strain hardening on the damage evolution. And as you can see here in the upper visualization, the triaxiality in the forming zone decrease with higher extrusion strain. And for both cases, SEM measurements have already been performed. And with a lower triaxiality, which represent the hydrostatic stress, we would expect that the damage evolution is in general lower or even not existing, so that it leads to some void closure mechanisms because we have a higher compression loading state, which leads to void shrinking. To obtain information about the real void distribution in terms of void error fraction, the extruded parts have been polished or cutted, then polished and etched, as shown in the area of interest, and especially the area on the central axis has been measured. And as you can see on the right hand side, with extrusion strain of 0.5, we have some voids which are embedded in the mangan sulfide environment, and in general also inclusions are included within such voids. So sometimes it's quite challenging to distinguish between a void and an actual inclusion. On the right hand side we also see some void, but this void is really small, and most of the void is filled with some inclusion. And this is also what we have expected. So we have less voids in the extrusion strain of 1.0 as for extrusion strain of 0.5. So we can say at the end that larger void nucleation for smaller extrusion strain occurs, but no significant change in the growth rate has been observed. After we have separated each mechanical properties from each other, and we now know how the strain, extrusion strain affect also the stress state, we can now have a look on the influence of damage on the product performance. Therefore, we manufactured the specimens out of the extruded parts and conducted, for example, tensile tests to measure the apparent Young's modulus in terms of the stiffness evaluation. And on the right hand side, the results of the apparent Young's modulus for different process parameters is shown. In the previous slides, we only considered the extrusion strain and the die cone angle or shoulder opening angle, but an additional process parameter is also the counter pressure, which has not been introduced yet. But with the counter pressure, we can also control the damage without affecting the strains hardening as well as the residual stresses. Beginning with these through bars, by applying a counter pressure, we can decrease the maximum triaxiality as shown here with the red dot. And this directly corresponds with an increase in the apparent Young's modulus. So these three specimens only differ in the damage, and the one with a higher counter pressure has less damage and a higher apparent Young's modulus. So we can say that with less damage the stiffness is higher, and this also holds for different shoulder opening angles, as you can see. But it's hardly to determine if different extrusion strains has in terms of the damage, positive impact on the apparent Young's modulus, because these two specimens cannot be compared with each other because the strain hardening is different. Then additional investigations has been done in terms of the impact energy. Therefore, some slightly other specimen geometry has been cutted out of the extruded parts with some cutting edge in 45 degree. And afterwards, these specimens were fractured by a hammer with an initial position, which then fall to the specimen and fracture or deform the specimen. And afterwards, the impact energy has been measured. And as you can see on the right hand side, we have in black the line for the maximum triaxiality. So with different shoulder opening angles, we can control the maximum triaxiality, and with an shoulder opening angle of 90 degrees, we have a higher triaxiality, which then leads to higher damage evolution and less impact energy. So we can say with higher damage, we have less amount of impact energy until the specimen fracture. Last but not least, also the fatigue life or fatigue strength has been investigated for the extruded part. Here high cycle fatigue is considered with stress amplitudes which are increased by the number of cycles. And most important to have a look on is the blue line as well as the pink line. So where we have the same strain hardening but different shoulder opening angles. So as we have seen before, with a higher shoulder opening angle, we can achieve higher triaxiality, leading to higher amount of damage. And therefore the shoulder opening angle of 30 degrees has less damage. And as you can see here, this specimen has a higher fatigue strength and therefore exhibits a higher number of cycles until the fracture occurs. Within the bulk metal forming round, not only the caliber rolling and the forward rod extrusion has been investigated, but also the flat rolling. To this end, RVE simulation considering the specific loading path of flat rolling has been considered, and different void shapes, elliptical, cylindrical shapes, as well as the location has been investigated. And it was found that the void volume decrease over the equivalent strain, but also the roll diameter as well as the path reduction has a huge impact on the void closure itself. And this is very important for subsequent manufacturing processes on forming processes, as with a higher void closure or less void volume, also the void evolution in the subsequent path might be less high. In terms of the product performance, additional experiments have been performed. So the damage were quantified by density measurements here on the left hand side, and the performance has been investigated in terms of the fatigue life. And as you can see here, with a higher density, with a slat thickness of 3 millimeters, for example, the number of cycles until failure is also higher.